Can you see my screen? Is it visible? Okay. Okay. So we will start this tutorial session. Okay. So yesterday we have started with the discrete time Fourier transform, that is DTFT. And we said that if I want to convert this natural frequency domain, values in the natural frequency domain into the frequency domain, then I will apply the DTFT. And if I want the natural domain values or sequence from the frequency domain, then in that case I can do the inverse DTFT and I can get the natural domain values. Okay, so we have also seen how to apply the DTFT formula and the inverse DTFT formula. So basically this is the transform. Transform is what? This is transform. Just a second. In this transformation, so we are transferring natural domain to the frequency domain. So this is basically a mapping of this whole paradigm. Like we are talking about the digital signal processing, where we are having the digital signal in is input to the discrete system. So suppose I say I'm having linear time invariant system, which transfer function is nothing but the impulse response of the system. Okay, and I'm having the input x of n. I say I will get output y of n from this system. Okay, so basically transform means what? We are doing the transformation on x of n. So after doing transform, I will get capital X of omega. For the system, I will say capital H of omega. Output is capital Y of omega. So I am transferring all these values in the frequency domain. Okay. Now the yesterday we have seen the example where this transform is useful. So one of the application is filtering. If I want to extract the particular frequency from the signal or system, and if I want to eliminate those frequencies, then I can easily do with this discrete time Fourier transform. Okay, so in this case, you can see here y of n or y of x. I can say that this y is nothing but what? This y is output is nothing but the system transfer function into the input. Okay, y of n is nothing but h of n into x of n. Okay, now today we will go through some properties of this. Okay, so uh, these are the properties you can see here. The list of properties, the time domain representation, and this is the frequency domain representation. Okay, so this DTFT is basically a linear. So linearity means this should follow the two principle. One is the homogeneity. Homogeneity means if I multiply this uh, sequence to the constant term, so at the output also I will get this constant term multiplied to that particular output. Okay. Now the homogeneity and additivity should be followed in the linearity. Okay. So if I'm having a times h1 n plus b times h2 n, then after doing DTFT, I should get this response a times h1 omega plus b times h2 omega. Please understand the notations. Here in the time domain, this is small h and small n. Here in the frequency domain, it is capital H. Okay. So when I do uh, the TFT over H of n, So I will get h of omega. Okay, for h1 I say h1 omega. Okay, like that. This is the property, linear. So DTFT is linear. Okay, then the time shifting. Time shifting means if I shifted time in the time of signal in the time domain, like instead of h of n, if I shifted this h of n by nd, some delay nd, then in frequency domain it is basically multiply with the e to the power j omega nd. Okay, so this you should understand. If it is delayed by some delay nd, then to the original DTFT output, I should multiply this term e to the power minus j omega nd. This is called a time shifting. In case of frequency shifting, frequency is e to the power j omega naught n. What is the frequency term here? Omega naught is the frequency term. If it is frequency shifting, that is e to the power j omega naught n, then in frequency domain you will get h to the h in of omega minus omega naught. So this frequency output also shifted by omega naught. Okay, then time reversal. Time reversal means if I'm having h of minus n, then in the frequency domain it is basically equal to h of minus omega. Okay, you can also easily prove this. Like h of minus n means what? This phase is rotate in the opposite direction. Here we are talking about the rotation to the power j omega. Okay, so this h of minus n means the phases are rotates in the opposite direction. Okay, so h of minus n basically maps to h of minus omega. Like if I apply dtft over h of minus n, so what is the formula? Summation of n equal to minus infinity to infinity, x of minus n. Instead of x of n, I need to write x of minus n. Okay, then e to the power minus j omega n. Okay, so if you put the minus n is equal to m, if you put the value minus n is equal to m, so what you will get? You will get n equal to minus infinity to infinity x of m. Here you need to write m. Okay, e to the power minus j. Now this is minus omega into m. So this is basically what? This is nothing but x of h of minus m. H or x. Here we have used x. So this is x of minus m. Minus omega, sorry. So like this you can also prove this. Okay, so please, and we will use these properties in our numerical examples. So this is about the time reversal. Okay, now the differentiation. So differentiation means in time domain it is multiplied by the factor n. If the signal or sequence is multiplied by factor n, so in frequency domain it is basically j times dt d omega of h of omega. That is derivative of h of omega, d omega. Derivative with respect to omega. Okay, not time. This is derivative with respect to omega. And it is j times this. Okay. This is j times the d omega, d of d omega. Then the next property is convolution. If H1 signal is convolved with the H2 signal in the time domain, then in the frequency domain, it is basically the multiplication. So it is basically equal to multiplication in the frequency domain. So we will directly multiply H1 omega with the H2 omega. Okay. If there is a multiplication in time domain, so this is basically equivalent to the convolution in the frequency domain. Okay, vice versa. If it is convolution in time domain, then it is multiplication in frequency domain. If it is multiplication in frequency domain, then it is convolution in the time domain. Okay, so these are the properties of the DTFT. Then one more important property is symmetry. Symmetry. Okay. Now in symmetry, basically, what is e to the power minus j omega n? E to the power minus j omega n is basically equal to cos of omega n minus of j sine omega n. This is the trigonometric function. Okay. So I'm having x of n. So after applying DTFT or inverse DTFT, I will get this x of omega. Okay, vice versa. Therefore, I have shown it with double arrow. X of minus n is what? X of minus omega. Okay, x convolution of n is nothing but what? X convolution of omega. Okay, now e to the power j omega n is nothing but cos of omega n plus j times sine of omega n. This is important trigonometric formula. Okay, if it is minus here, in case of minus, you need to put here minus. Okay, now we know the standard formula of DTFT, discrete time Fourier transform. So if you put the if you expand this term e to the power minus j omega n, so instead of this I can write cos omega n minus j times sine omega n. Okay, now from this I can easily separate the real part and imaginary part of the signal h of omega. Okay, now real part is what? Summation from this minus infinity to infinity h of n into cos omega n. Okay, and imaginary part is what? Minus of this minus sign is important, summation over h of n into sine omega n. Okay, now we know that cos of omega n is nothing but cos of minus omega n. This is equal, but in case of sine, sine of omega n is what? Minus of sine minus omega n. Okay, otherwise you can say that sine of minus omega n is nothing but minus sine of omega n. Right, now we can split this h of omega in even and odd. We can separate this even part of h of omega and odd part of h of omega. Now in the HR real part of omega, we are having the cos function here. We are having the cos function. Okay, so cos basically is what? The even function, because cos of omega n is nothing but cos of minus omega n. Therefore, HR of omega is equal to HR of minus omega, I can say. HR means the real part of the h of omega. Okay, so therefore this is even function, and imaginary part is basically this is equal to minus of hi into minus omega. This is the odd function. Okay, so I can split this h of omega in even and odd function. Okay, Now this H convolution of omega, H star of omega, which is conjugate of this, is basically equal to H of minus omega. Conjugate of omega is H of minus omega. This is equal. Okay. Now suppose I want to find the magnitude and phase spectrum for this H omega. Then I can write like H of omega, magnitude of H of omega is equal to the magnitude of minus H of minus omega. Okay, this is the same. Now magnitude, if this is correct, then you can say this magnitude is the even function. You will get the even function there. And in case of phase, what will happen? In case of phase, angle of H of omega is nothing but minus of angle of H of minus omega. Or in other word, angle of H of minus omega is nothing but minus angle of H of omega. Okay, angle or phase you can say. So you can say that magnitude is even and the phase is odd quantity. Okay. Now symmetry, therefore it is symmetry property. We are saying the symmetry of the signal. Okay. So the real part is even symmetric. The odd part is the real imaginary part is the odd symmetric. Okay. Similarly, in case of magnitude and phase. Now, if you see these plots, now this is the plot for real part of omega. This is the imaginary part of omega. This is the magnitude of h of omega, and this is the angle of h of omega. Okay. Now, in this case, if you see this, what is this function? This is the even function. This is the odd function because this is same along this y-axis. Okay. And this is negative of this real part. Okay. Again, in case of magnitude, it is this is even and this is odd. Okay. So we have already seen here that the real part is even symmetric, the odd part is the imaginary part is odd symmetric. Therefore, these are the correct shape of the frequency response of the h of n system. Okay, now look at the graph below. Okay, what about this? This is, can you see any symmetry here? No symmetry. Here, this is, you can say along this y-axis, this part is same. Therefore, this is even function. This is this is not symmetric. This is again even symmetric. Okay. So this is not following our previous symmetry property of the DTFT. Okay. So therefore, I can say these are the false shape of the frequency response. These are not the correct shape. Okay. So what symmetry property says basically, so if I'm having the real signal in time domain x of n, so in frequency domain, this x of omega is nothing but x conjugate of minus omega. The real part is nothing but xr of minus omega. The imaginary is minus of xi of minus omega. The magnitude is same and this is the same. Okay. So this is the symmetry property. Okay. Now, if I'm having the real and even signal, real signal is basically the even signal. So if I'm saying this is x of n, which is real and even. Real and even. Real means what? I will be having only cosine term. Okay, and even signal means I can write this x of n is equal to x of minus n. Okay, now what will be the frequency response for this type of real and even signal? So I can say this is the x of omega, which is equal to xr of omega. Okay, because I'm saying this is real, therefore I have put here capital R. Now basically what we do summation over minus infinity, n is equal to minus infinity to infinity. Okay, now this I can split like this. So x of n, suppose, so I can say summation, I can put x of 0 outside, plus I can say this is twice summation of from n equal to 1 to infinity. Okay, so therefore this is written like this, and this is real signal, therefore I have only taken the cosine term here. Okay, please understand this property, symmetry property. If the the given signal is real and even, then you only have to you will be having only cosine term. Okay, and this I can write 2 times summation from 1 to infinity. Otherwise you can write from n equal to minus infinity. Now we have already separated this x of 0, therefore you just write like this, then it will be easy for calculation. Now if oh, this real is not this real actually. Oh, just a second. This real means this is the just a real signal, natural domain signal. Okay. Now, if this natural domain signal is basically a odd signal means what? X of n I can write minus x of minus n. Okay. Now, if I say this is the odd signal means I will be having only the imaginary part of this. Okay. So this is equal to what? This is equal to minus j times this minus j factor is important. That is the j factor basically. Minus is already there. If you see the formula here, so minus is already there in case of imaginary representation. So this is already there. So we basically need to multiply by j. Okay. Again, this limit I can say that the summation is from minus infinity to infinity. So I can write 2 times the n equal to 1 to infinity. Okay. So sine of 0 is basically the 0. Therefore, this x of 0 is term is eliminated. So you can directly write minus j into 2 times this. Okay. Now we'll see one example here. Suppose I am having this real valued signal, which is h of n is equal to 2 times delta n plus 2 plus 2 times delta n minus 2. Can you represent this in graphical form? So this is n, this is h of n, suppose. Okay. So in graphical form, I can represent this like this. This is suppose 0, this is 1, this is 2, this is minus 1, minus 2. So we will be having magnitude 2 at n equal to minus 2. Okay. And at n equal to plus 2, again magnitude is 2. Okay, so this is basically symmetric along this y-axis. Okay, so this is even function. Correct. Now, first thing is what is asked here. to find h of omega. So h of omega we can easily find out. So I say that this is basically the even function. Therefore, I can directly apply the formula of real and even. Okay. So in that case, what we have said in symmetry property, this h of omega is nothing but what? hr of omega, which is h of 0 plus 2 times summation from n equal to 1 to infinity h of n into cos of omega. Correct? Now, basically, we are interested in this interval only minus 2 to 2 because it is represented in this span. Therefore, summation will go from minus to here, minus 2 should be there, minus 2 to 2. Okay, h of 0 is what you can here say. H of 0 is having 0 value, therefore it is 0 here. Okay, this is 2 times summation of this h of n. Now we have taken summation from minus 2 to 2 here. Okay, now again if you expand this, I will write this 2 times summation of minus 2 to 2 means h of minus 2 I will put keep outside, h of minus 2 into cos of minus 2 omega plus what is the next value is available in the given real valued signal at n equal to 2. Therefore, h of 2 plus h of 2 I can directly write into cos of 2 omega. Okay. Now h of minus 2 is having 2 value. 2 times cos of minus 2 omega is nothing but cos of 2 omega plus again h of 2 is 2. This is cos of 2 omega. Correct. So this is what 4 cos of 2 omega into 2. Correct, no? So I should get output 8 cos of 2 omega. Correct? So
Yes.
output should be 8 times cos of 2 omega. Oh, ho, 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 ho. No, 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 no. If I'm taking summation from minus 2 to 2, then this factor should not be there. 2 factor. Okay. If I'm taking summation from 0 to 2, in that case only I can put factor 2. Correct? If I'm saying this is summation 2 times summation, are you following me? Have you understood the mistake?
Can doctor explain it again?
So this is basically what in while calculating DTFT, we say that this is summation over minus infinity to infinity, right? And this we have expanded like 0 we have taken outside x of 0 and plus this is 2 times I say summation from 0 to 0 to infinite. Okay. Now similarly in our given sequence, which the interval given is from n equal to minus 2 to 2. Okay. So what will come here? N equal to minus 2, minus 1, 0, plus 1 and 2. Correct. Now if I take this 0 outside and this I will say that because this is the even function. So I will say that this is n equal to 0 to 2 but 2 times. Now understood?
Yes. Thank you, doctor.
So therefore it should be here 0 to 2 and 2 times. So what you will get here? So in the interval 0 to 2, you are having value at only n equal to 2. N equal to 1 is 0. 0 we have anyway keep outside. So I can say that this is equal to 0 plus 2 into h of minus h of 2 into cos of 2 omega. Okay. So h of 2 is what? 2 into cos of 2 omega, and this is again multiplied by with this factor 2, therefore you will get output 4 cos of 2 omega. Okay, so this is the answer for h of omega. What else we need to find? Magnitude of h of omega. So magnitude of h of omega, I can simply write magnitude in terms 4 cos of 2 omega. Okay, if I want to find the angle of h of omega, is nothing but what? Tan inverse of imaginary part by the real part. Imaginary part here is 0. Therefore, this will be having 0 if omega h of omega is greater than equal to 0. This is pi if this is less than 0. And if this is h of minus pi, then it is minus pi. Okay. If you want to find the magnitude in decibel dB, so you need to multiply the 20 log to the base 10 of the actual magnitude value. So you will get the magnitude in the decibel. Okay. Similarly, can you try this example? Now here, if you plot these, so here I'm having n, and this is suppose h of n. Now this is 0, this is 1, 2, minus 1, minus 2. So at n equal to minus 2, I'm having 2. Okay, and at n equal to 2, I'm having magnitude minus 2 here. Therefore, this is minus 2. Okay, now this function is basically the odd function. Okay, now in that case, you can find out h of omega like this: minus j times 2 of j times 2 into summation from n equal to 1 to infinity h of n sin omega n. But here again, we are interested in only up to 2. So 2 times n equal to 0 to 2, this. Okay, so what you will get output? Minus j times 4 sine omega 2 omega. So the magnitude is this. Then the angle you can find, this is the tan inverse of imaginary part by real part. So if omega is greater than 0, then this is sine of 2 pi. So you will get the angle minus pi by 2. If omega is less than 0, so in that case, since this is negative sign here, so in that case, you will get pi by 2. Okay, angle pi by 2. Now, similarly, if I'm having, if I need to calculate the magnitude in dB, so you need to multiply 20 log to the base 10 to this magnitude value. Okay, so this is the simple example of this. So please practice this example at home. And if you are having any doubts related to this, then you can ask me. Okay. Now we'll take one more example. I say example 3. So suppose I'm having x of n equal to n into alpha to the power n u of n plus 2. And I say that this alpha is mod of alpha is less than 1. This is given. Okay, in that case, find h of omega. Oh, sorry, x of omega. This is x, no? So find x of omega. Okay, now how to solve this? Now we know that alpha to the power n u of n. What is the DTFT of this? If you solve this, you will get this 1 divided by 1 minus alpha e to the power minus j omega. Okay, now x of n, so this is basically delayed by 2, like n alpha to the power n into u of n. This is basically, now in our case, this is u of n plus 2. So before u of n, we are having two more values, that is n equal to minus 1 and minus 2. Okay, so minus 1, minus 2, then u of n, and that will continue. So this x of n, the given x of n, I can split like this. So I will say that n equal to minus 2, this is alpha to the power minus 2. At minus 1, this is minus alpha to the power minus 1. And rest are n into alpha to the power n u of n. Okay, so I can split these like this. Why? Because this is in advance of 2, not delay. This is in advance of 2. So you were in the step u of n is nothing but the step signal. So in the u of n is started with n equal to 0. Okay, so you will be having magnitude 1 for n equal to greater than equal to 0. But u of n minus n plus 2 is what? If you are having values, that means u of n is having magnitude 1 for n greater than equal to 0, 0 otherwise. Okay, so u of n plus 2 is what? Will be having magnitude n for n greater than equal to minus 2. Okay, if n is less than minus 2, you will be having magnitude 0. Correct. Therefore, this given signal, I have split it like this. Okay, now I will find the corresponding frequency response for each one of this. Okay, so I will say that h of omega is basically equal to, if I apply Fourier transform over this, what will I will get? So I will get minus 2 e to the alpha to the power minus 2 into e to the power j to omega. Okay, then here minus sign because we are adding, because we are doing summation over this. Therefore, I can directly write minus alpha to the power minus 1 e to the power j omega. plus this is n times alpha to the power n u of n. Okay. Now the dTft of this term, dTft of this term is what? This is basically equal to 1 by 1 minus alpha e to the power minus j omega. Now in time domain, if it is multiplied by n, then in frequency domain, it is basically the derivative. Therefore, this entire term I can write like plus j times d omega of 1 by 1 minus alpha e to the power minus j omega. Okay, so are you getting my point? So what is the dTft of this? Okay, so the dt of ft of this I can write like this. Now this is basically equal to what? 2 minus 2 times alpha minus 2 e to the power j 2 omega, alpha minus 1 e to the power j omega, plus j times this is, if you do the derivative of this, what you will get? This is 1 minus alpha e to the power minus j omega whole square, and derivative of this term. So this is basically alpha times e to the power minus j omega. Okay, so the final result is basically this. Okay, so this is the final answer for this. Have you understood this example? So given a sequence like this, if I want to find the h of x of omega, so you have to go like this. Have you understood this example? Is there any difficulty in this? Yes, students?
I think should be fine now, doctor.
This is fine? Okay.
More maybe
Sorry?
we can fully understand that.
Sorry, what you said?
Maybe after we some maybe after doing more can fully grasp the all of these ones.
You need to
But for now, should
practice the examples. So you can take this book, the reference book I suggested. So at the end of that discrete time Fourier transform chapter, you will see many examples to practice. Okay. Where is my book? So at the end of chapter 2, you will see the problems to practice. Okay, you can go through that. So have you done the quiz yesterday?
Yes, doctor.
Is there any difficulty in that?
yeah, doctor.